Good day, everybody. Today, we'll be talking about organic chemistry. Organic chemistry is carbon-based chemistry. It studies the structure, properties, and the reactions of organic compounds, which contain carbon in the covalent bonding. Why carbon? Because carbon is very special. First, carbon is versatile because it can form different types of bonds. For example, it can form single bonds, double bonds, triple bonds. It can also form different shapes. For example, it can form chains, branched chains, and the rings when they connect to other carbon atoms. Another important property about carbon is tetravalent, which means carbon can form 4 single bonds or equivalent of that. For example, a carbon can be surrounded by 4 single bonds. Carbon can be surrounded by 2 double bonds, which is equivalent of 4 single bonds. Carbon can be surrounded by a single and a triple, or carbon can be surrounded by a double and 2 single. So this provides versatile bonding structure and also different shapes. When we talk about the molecular shape or so-called molecular geometry, according to what we have already learned when we do Lewis structure, this center carbon over here would have a tetrahedral shape. And this center carbon, the second one, would be a linear shape. Then the third one also has 2 bonds with no lone pairs surrounding it. It's also a linear shape. And the last carbon center would be trigonoplanar. So as you can see, carbon is very versatile in terms of different types of bonding and in terms of different shape. And also, as you can see, some is linear, as you see over here, some is branched, and some is even ring shape. As you can see in these 3 different structures over here, 1, 2, and 3, you noticed the carbon atoms are connected with each other to form different structures over here. And this property for carbons to connect with themselves is called a catenation or chain up. So this is another versatility shown by the so-called catenation of carbon atom, which means carbon atom can connect with themselves to form different shapes. Let's look at a few more examples. For example, in methane, carbon center is surrounded by 4 different hydrogens, and this will give you a tetrahedral molecular geometry or molecular shape. And surrounding this carbon center, you have 3 different bonds, one double and 2 single bonds, and with no lone pairs, which means surrounding this carbon center, you will have trigonoplanar geometry. And for the last example, as you see over here, this carbon is surrounded by a single bond on the left and a double bond on the right side. So for this carbon, it is surrounded by 2 electron groups with no lone pairs, which means for this molecular shape, it will be linear shape or linear geometry. Let's look at a practice question. Organic compounds always contain what element? Yeah, apparently this is a very straightforward question. Organic compounds always contain carbon in the structure. One of the most common type of organic compounds is called hydrocarbons. And hydrocarbons are the organic compounds that contains hydrogen and the carbons only. And it can be an alkane, a hydrocarbon can also be an alkene or an alkyne, which has different formulas over here. For example, if you have C₃H₄, and this would be an alkane, because this can be written as C₃H 2 times 3 plus 2. So this is an alkane. Right. For alkene, if it's unbranched, you would have CN H times 2N. Okay, H with 2N hydrogens. So for example, C₄H₄. Okay, and this can be written as C₄H2 times 4. So if it's unbranched hydrocarbon, this means it will be an alkene. All right. For an alkyne, give you one example. For example, C₃H10. Right. This has a structure. You can rewrite it as C₃H2 times 6 minus 2. So this is an alkyne. But do remember, if you have such a common formula as you see over here, it does not guarantee there will be a certain type of hydrocarbon. For example, if you have C₄H₄, it can be an alkene. It can also be a cyclic alkane. But for more details, we can talk about this later on. Let's look at one more question. Which of the following is not a hydrocarbon? Do remember, what is hydrocarbon defined as? Hydrocarbon contains hydrogen and the carbons only. So this one has carbon and hydrogen, so it is a hydrocarbon. This one has carbon, hydrogen, and oxygen. No, so this one is not a hydrocarbon. Here, the third one is carbon, hydrogen only, so this is a hydrocarbon. This one is carbon and chlorine, so it's not a hydrocarbon. That's A and C are correct. That's why we pick E, 2 of above. All right. Which of the following is an alkane? Remember, alkane has a common formula like CnH2m plus 2. All right. So the first one, when you rewrite it, it can be written as C1H2 times 1 plus that 2. So this one is that N in this formula. Right. So this one is an alkane. This one is correct. Look at the second one. It can be rewritten as C3H2 times 3 plus 2. So this is also an alkane. Now you look at the third one. You rewrite the formula. It gives you C6H6. So it can be rewritten as C2H2 times 2 plus 2. So this is also an alkane. D, you rewrite it. It will be C8H2 times 8 plus 2. So that's also an alkane. So for this reason, all of above is the correct answer. What type of hydrocarbon is C2H2? Again, do remember we have 3 different types of hydrocarbons with corresponding common formulas listed over here. An alkane, it's CnH2m plus 2. Alkene is CnH2n. And alkyne is going to be CnH2m minus 2. So when you rewrite this formula, C2H2, it could be written as C2H2 times that 2 minus 2. So this is the N, right? This 2, number 2, is that N. So this is the same as Cn2n minus 2. So this is an alkyne. Let's go into the details about alkanes. In alkanes, all bonds are single bonds. when you have all bonds, all covalent bonds being single bonds, we call this structure to be saturated. There is no double bonds or triple bonds. So we call this type of hydrocarbons saturated hydrocarbons. Alkanes are saturated. As you can see in the example of methane, which has a formula of CH4, when you write the Lewis structure, okay, you have one carbon surrounded by 4 single bonds, which connects to 4 hydrogens over here. So this is the most simple alkane, which is called methane. All right. Let's look at a couple more examples over here. When you look at butane, you have 4 carbons. 1, 2, 3, 4. 4 carbons. We'll talk about the nomenclature in more detail later on. So butane means you have 4 carbons surrounded with enough hydrogens. How many hydrogens should you have? Do remember, carbon is tetravalent, which means carbon forms 4 single bonds. So carbon is surrounded with 4 single bonds. So for terminal carbon, you would need to have 3 more hydrogens because you already have a single bond connected between carbon and carbon. Okay, we'll go over the details later on. But you look at, it's all single bonds. So this is an alkane, as you can see in the formula, because C₄H10 can be written as C₄H 2 times 4 plus 2. This is all single bonds. It is an alkane, a saturated hydrocarbon. All right. So when you look at the formulas over here, we have different formulas. The formulas you see, this one is so-called a chemical formula, which combine all elements of the same type. The structural formula is a shorthand way of writing a structural formula in which you eliminate many of the other bonds and group hydrogen and atoms together on each carbon. Remember, condense the formula. For example, for this carbon, you have 3 hydrogens. So we condense that together, it becomes CH3. Now for the next carbon, on that carbon you have 2 hydrogens, so it becomes a CH2, right? Then this carbon has 2 hydrogens, so you put it as CH2. The last hydrogen, carbon here, you have 3 hydrogens on it. So this structural formula, when you condense the hydrogens on the same carbon, it becomes so-called a condensed structural formula, or you can simply call that condensed formula. Both are the same. Okay, condensed structural formula and the condensed formula, they are the same thing. Let's look at another example. For example, you have a compound that has, let's say, a structure like this. So first we write the carbon skeleton first, and then we are going to fill the vacant positions around the carbon. So how many hydrogens do you have around each carbon? There's one key information we should know. Carbon is tetravalent, so this particular carbon has 1 single bond connected to it already. Carbon is tetravalent, so you need 3 more single bonds to fill up the position. So these 3 single bonds will be the number of hydrogens you need. So it will be saturated. When you look at the next carbon over here, this carbon is surrounded by 1, 2, 3. 3 single bonds already. Carbon is tetravalent. You need 1 more bond, and that is connected to 1 hydrogen. You look at the terminal carbon over here. You have 1 single bond surrounding this carbon, so you need 3 more hydrogens to make it tetravalent. Similarly, for this carbon, you need 3 more hydrogens. So this structure, which has all carbon, hydrogen connected with a covalent bonds, and this type of structure is so-called structural formula. if you condense the hydrogen on each individual carbon, for example, on this carbon, you have 3 hydrogens, so we put it down as CH3. The next hydrogen, the next carbon, has 1 hydrogen on it, so you write it that way. Then the other carbon over here, you have CH3 as well. Now on the middle carbon over here, or the middle carbon here, it's connected with a CH3. So we write a vertical line to represent a single bond connecting with the CH3 group. And this structure, as you see over here, this structure will be called the condensed formula. This is the condensed formula, or condensed structural formula, the same thing. For the alkanes that have no branches, or the alkanes with straight chain, we call them normal alkanes. For example, if you have 3 carbons over here and they are forming a straight line, and you put down the number of hydrogens on it, so that's so-called normal alkanes. That's the structural formula. We can also write the condensed formula, which saves time. Okay, all right. Let's look at a whole series of normal alkanes. Methane, we have 1 carbon inside. Eth means 2 carbon. Prop means 3 carbon. Bute means 4 carbons. Pent means 5 carbons in straight line. And hexane, 6. Hept, 7. Oct, 8 carbons. As you can see, as the number of carbons increases, the boiling point increases. So methane, ethane, propane, and butane are all gases at room temperature, but starting from pentane, it becomes a liquid because the boiling point is above room temperature, which is typically 25 degrees C. Pentane is a liquid at room temperature. Not all alkanes are normal alkanes. Some of the alkanes will be branched alkanes. For example, isobutane is branched because you don't see a straight line. The normal butane would be 4 carbons connected together with correct number of hydrogens surrounding each carbon. This is the structural formula for so-called normal butane, or simply butane, with the corresponding condensed formula as you see over here. All right. But you can also write a different structure as you see over here. Now will be, you have, rather than having 4 carbons in the chain, we have 3 in the main chain, and the 1 carbon is connected to the center atom, and then you add a correct number of hydrogens. Okay, let's just do it in the condensed formula way. So CH in the middle and CH3, then you have CH3 over here. You see, so this has a main chain which forms a straight line, and you have a branch. So this type of alkane is called a branched alkane. And as you might have noticed, if you write the formula for the compound on the left side, you will have C₄H₁. When you look at the right side, it also has the same formula. So if 2 compounds or more compounds have the same chemical formulas but have different connectivity between atoms, we call them isomers. So those 2 compounds listed over here, they are so-called constitutional isomers because they have different connectivity between atoms. So far, we have used different names for different alkanes, but how do we really name these alkanes? So let's talk about it. When you try to systematically name alkanes, the first step, you try to determine the base name. So what is base name? base name tells you the number of carbons, okay, the number of carbons in the longest continuous carbon chain, okay. And we also, after the base name, in the base name, you put an ending, ANE, for alkane. You see, alkane has ANE ending. So for the name of an alkane, you also have ANE ending. All right. For example, if you have one carbon, which is surrounded with 4 hydrogens over here, right? You can also simply write it as CH4. It has one carbon. One carbon corresponds to a prefix of meth. But do remember, since this one is an alkane, because it's a form, it's the same as like a C₁H₂ times 1 plus 2, right? So this is an alkane. It's saturated. It's all single bonds, as you can see. So this is an alkane. So you will also have an ending of ENE. So methane. So that's how you name this CH4 over here, right? Eth means 2 carbons. For example, you might have a CH3 and a CH3. This will be called ethane because you have a 1, 2 carbons, and they are all single bonds. How do you know? Because if you spread out the hydrogens, you will know each carbon have 3 hydrogens, and they are connected with single bonds with the hydrogens. So it's 2 carbons in the main chain. Okay, so that's why you use eth. And yet all single bonds, that means it's ethane over here. All right. So I will give you more examples later on. If it's 3 carbons, you use propane, 4 bute, then 5 it's pent, etc. You need to memorize all these prefixes. That's the first step. Determine the longest continuous carbon chain. Longest continuous carbon chain. Second step, you need to decide the branch name and the position number. Anything that is not part of the main chain, or it's not part of the base, if it's not a part of the base or the longest carbon chain, which is also called a main chain, if it's not part of the main chain, it will be the branch. So when you do the branch name, it's slightly different. Okay, so basically the branch will always have EL ending. You see, the branch names always have EL ending. 1 carbon branch, you call that a methyl, because meth means it's 1 carbon. Ethyl, that means 2 carbon branch. Okay, propyl, that means 3 carbon, 1, 2, 3, etc. Okay, you also have some names like isopropyl. Propyl means 3, but iso we use to refer to the specific structure. Okay, and for example, tert-butyl, or you can simply call this T-butyl group. T-butyl group has 4 carbons, 1, 2, 3, 4, but it's structured in this specific way, right? Step 3, you write the name of the compound in this format. You write the branch number or branch position first, then you write the branch name. In the end, you write the base name. Okay. Number 4, if a compound has 2 or more identical substituents, designate the number of identical substituents with the prefix di to represent 2 and tri for 3, tetra for 4, etc. Let's look at some examples so you have more idea about how this works. For example, look at the structure listed over here. The first step, we find the longest continuous chain as the base. So here's the longest chain. When you look at the structure, here's the longest chain. In this longest chain, it has 1, 2, 3, 4, 5 carbons, and it's all single bonds, so it's an alkane. So 5, you use pent to represent it. So this base name, you write down the base name first. It's called a pentane because it's an alkane. Now we're going to do the branch. Anything that is not part of the circled portion, it's called the branch. So this is a branch. That is also a branch. Let me circle it as well. Okay. So that's a branch, and this branch is called a methyl. You're going to give it a name for the second step. Okay. You're going to give it a name as well for methyl. Not only you need to give it a name, you also need to give it a position number. What do you mean the position number? The position number means on which carbon of the main chain the branch is attached to. So here's the main chain. We need to number the main chain. We have 2 different ways to do it. You can start from one end or the other. For example, if you start from this end, it's 1, 2, 3, 4, 5. So you will notice on carbon 2 over here, on carbon 2, this methyl is attached to carbon 2, and the other methyl group is attached to carbon 4. So for this reason, we write down the position number over here, so it becomes 2, 4. You have 2 different methyl groups. It becomes dimethyl pentane. Let's look at a few practice questions. First one, how many structural isomers can the formula C₂H₂ have? I strongly suggest when you try to write the structures of any formula, write the carbon skeleton without hydrogens to begin with. Then you can fill it up with enough hydrogens according to the tetravalency of carbon. For example, when you write the structure of carbon C₂H₂, the first structure you could expect to have would be having all 5 carbons in the same longest chain. Or you can have 4 carbons. But do remember, if you write the next carbon on the first one, that's not different because the last one is still part of the main chain. You can do zigzag and you can put it down, but this is the same thing. So this is not a different structure. So that's not different. But you can actually put a carbon as the branch like that. Or you can have 3 carbons in the main chain, then 1 at the top, 1 at the bottom. So with the carbons only, or the carbon skeletons, you can write 3 maximum number of structures. You might be tempted to write, for example, say, hey, how about I have 2 carbons in the longest chain. Then you're gonna, where are you gonna list the other 3? It must be connected somewhere. If it's connected to over here, hey, that's not. Then 3 would be at least the longest chain. It would not be 2. Did you see? Where can I list the other 3 carbons? No matter how you list it, you will see the longest chain can never be 2 carbons. So that's why this one is not a valid one. It will be the same as one of the structures we just listed over here. Okay. So you do know we have 3 isomers over here because they will have exactly the same formula. But if you want to fill this up with the correct number of hydrogens, you can do that. Remember, carbon is tetravalent. So if carbon is connected to 1 single bond, as you see over here, this carbon would need 3 more hydrogen. That's why you might write CH3. This carbon is connected with 3 single bonds, so you need 1 more hydrogen. This carbon has 2 single bonds surrounding it. That's why you need 2 hydrogen. And the last carbon on the right side, you have 1 single bond, so you need 3 more hydrogens over here. The bottom one, 3 more hydrogen as well. Then we do it the same way to fill up the number of hydrogens for each carbon. So from the carbon skeleton only, we are able to quickly identify the 3 and only 3 isomers for this formula, which has 5 carbons inside. So the take-home message is to quickly write down the formula, the structural formula, from the common chemical formula, you write the carbon skeleton first. Then in the end, you fill up with corresponding correct number of hydrogens according to the tetravalency of carbon. Let's look at the next question. How many carbon atoms are in tert-butyl alkyl group? Basically, T-butyl group or tert-butyl group. Has a structure like this, a carbon connected with 3 methyl groups. Okay, the question mark means it's connected with another structure, but this is called a T-butyl group. You see, it's a butyl. Okay, T-butyl. Sorry, it's called a T-butyl group. Okay, so it's 4 because but means it's a 4. What is the name of the following compound? So basically, let's name this hydrocarbon. Remember, we see single bonds only in this structure. That means this is an alkane. So you should have A and E ending. For all the 5 choices, you do have A and E ending. But now you got to identify which chain is the longest chain. So you might think, oh yeah, that's the longest chain. But let's count the number of carbons over here. 1, 2, 3, 4, 5, 6. So this one has 6 carbons. Okay. Now I can actually draw the chain like this way. You look at this one. Let's count how many carbons are inside that chain. 1, 2, 3, 4, 5, 6, 7. Okay. You can keep trying and you'll find out actually for this structure, if you count the number of carbons, you know it has 7 carbons. So the 7 carbon is longer. You're going to use the 7 carbon as the base. So for this reason, it will be base name 7 carbon. So it's hept. It's an alkane which has A and E ending, so it's heptane. That's the base name. But we're going to put before the base name the branches. Okay. So what are the branches? This is one of the branch. This is also one of the branch, and this is called a methyl group, because it's 1 carbon. So this is also methyl group over here. But you also need to identify the position number for the branch. So if you count from this end, this is carbon 1, carbon 1, carbon 2, carbon 3, 4, 5, 6, and 7. So the first branch you actually, we have 3 branches. You see, we have another branch over here. Did you see? So this is also another methyl group. Okay, but do remember, you always have other possibilities, right? For this possibility, it's on carbon 2. You have 1 methyl group. You see this carbon 2. You have 1 methyl group, and then on carbon 3, this carbon, you have another methyl group. Then on carbon 6, you have the 3rd methyl group. So it would be, when you rewrite it, it would become, this one is on carbon 2, so it's 2 dash. And then here you have 3 dash. Here you have a 6 dash. If you number the carbon in the main chain in the wrong way, for example, what if I number the carbon over here as number 1, then you keep going backward, you would have a number like number 1, number 2, number 3, number 4, 5, then you would have carbon 6 and the carbon 7. So then the number system will be different. For example, then this one, rather than being 6-methyl, it would be 2 because it's number 2. So the second would give you 2-methyl. Okay. Then over here, this carbon would be number 5. So it would become 5-methyl. Then this methyl group would be on carbon 6 rather than 2. So you would have another like a 6-methyl. So you have two different ways to do it, but there's only one way is correct. So which one is correct? So when you do the first one, the branches are on carbon 2, you see carbon 2, carbon 3, and the carbon 6. So it's 2, 3, and 6, trimethyl. So the first way would give you a name like 2, 3, 6, trimethyl. You got to put the methyl group together, so it's called a trimethyl heptane. Then the other one, if you follow the carbon numbering from the top, 1, 2, 3, 4, 5, 6 over here, you would have 2 and 3 and 5 and 6 actually. So the other one, according to the name, it would be 2, 5, and 6 trimethyl heptane. So which one is correct? Remember, you want to make sure the branch has the lowest possible position number. So this 5 is a higher number than 3, and everything else is the same. So the first one is correct. The second one is wrong. So this compound is named as 2,3,6 trimethyl heptane. So E is the correct answer. The bottom one is the wrong name. So far, we have worked on many examples of alkanes. Let's look at the other two types of hydrocarbons, which are the alkenes and alkynes. For alkenes, it contains the double bond, and alkynes are the hydrocarbons that contains at least one triple bond. It's carbon-carbon triple bond in alkyne. Alkenes, you will contain CC double bond, right? Because in the CC double bond, you can actually react with more hydrogens, so we call them unsaturated hydrocarbons. And alkenes will have the formula CnH2n, and alkynes will be CnH2n-2. Let's look at some examples. For example, ethene. When you look at eth, that means it's 2 carbons, as you see over here, 2 carbons, and E in the structure. You do see a CC double bond. Propene, prop means you have 3 carbons, and E means you have a CC double bond. As you can see in the structure, you have a CC double bond. You also have 1, 2, 3 carbons. So that's why it's called a propene, right? What about 1 pentene? Pent means it's 5 carbons. 1, 2, 3, 4, 5. 5 carbons. And ENE means you have a CC double bond. So what is this 1? This 1 means that's where the ENE is, where the double bond is. The double bond starts with carbon number 1. So that's why you put a 1 before the whole thing to indicate where the CC double bond, or where the functional group, CC double bond is a functional group, so where the double bond is. We will talk about the naming for alkenes and alkynes shortly. Let's look at some examples of alkyne. Alkyne, when you look at all the structures over here, they all have YNE ending, which means you have a CC triple bond in all the alkynes with YNE ending over here, CC triple bond. And for example, 1 pentine, pentine means you have 5 carbons, 1, 2, 3, 4, 5. Similarly, the number before the whole thing indicates where the triple bond is. So 1 means the triple bond started with carbon 1. So let's look at the naming for alkenes and alkynes. The name for the alkenes and alkynes, they are almost the same as the alkanes with a few exceptions. For example, when you pick the base chain, it's not going to be the longest continuous chain. Rather, it's the longest continuous chain that contains, it must contain the double bond or triple bond. You must make sure the double bond and triple bond is part of the main chain or the longest continuous chain. Okay. The second thing is the base name will have E as the ending for alkenes and Y for alkynes. Remember, for alkanes, you do have ANE ending. All right. Number 3, the base chain is numbered to give the double bond or triple bond the lowest possible number. Remember, for alkanes, we want to make sure the branches have the lowest possible number. But over here, for the alkenes and alkynes, you make sure the double bond or triple bond have the lowest possible number. And the position number, you're going to insert a position number of the double bond or triple bond just before the base name. For example, when you have a structure on the left side, this one has 1, 2, 3, 4. It has 4 carbons, so that's why you have a but to represent 4. All right. It also has a triple bond here, so that's why you have YNE over here. And you also need to indicate in step 3, okay, indicate where the double bond or triple bond is. This one, the triple bond is on position 1. Okay, you must make sure the triple bond or double bond has the lowest possible number. So that means if you number it differently, like what you see over here, if you put 1 here, 2 here, 3, 4, that will give you 3. That's where the triple bond is. This will give you 3 butane. That would be the wrong name because you want to make sure the triple bond has a lowest possible position number. In this case, 1 is the lowest possible number. All right. You look at the next example. The next example, first thing, you pick the longest chain that contains the triple bond or double bond. So that's apparent to the longest chain. This has 5 carbons. That's why you have pent over here. But you have a double bond. That's why you have ENE ending. Now you are going to name the branches as well. This is a branch. This branch is on position 2. And that's why you have a name as 2-methyl 2-pentene over here. Let's look at a few more examples. For example, you have an alkene over here. Why is it an alkene? Because you do have a CC double bond here. So this is an alkene. That means it will have ENE ending, not ANE. So ENE ending, ENE ending, ENE ending. But how do you name this compound though? So when you name this compound, do remember you must have the longest carbon chain which contains the double bond. So when you contain the double bond, that means this end must be included. Okay, so when you go either end, this is the longest chain. When you draw the other one over here, that's also the same number of carbons. So either way, it will be correct. Okay, so I'm going to erase this one. The longest chain will have how many? 1, 2, 3, 4, 5. It's 5 carbons. So the longest chain, you're going to write down the base name because it's 5 carbons. It's going to be pent. Since it's alkene, so you can have ENE ending. That's called a pentene. Now you're going to do the branch. So that's the branch. So on which carbon is the branch on? So you must number this from the right side, because that will give you a lower number for this double bond here. Okay, so that's why you put number 1 over here, and this will be number 2. So number 2, number 3, 4, 5. So you do know On carbon 3, you have an ethyl group. So it will be 3-ethyl. You put this together, it will become 3-ethyl pentene. So E is the correct answer. Let's talk about some reactions that hydrocarbons can undergo. One of the most common hydrocarbon reaction is so-called combustion, or burning off of hydrocarbons in the presence of oxygen. Okay. For alkanes, alkenes, and alkynes, they all undergo combustion. When it reacts with oxygen, it will form carbon dioxide and the water as the product. So for example, when you have a methane, it reacts with oxygen or burns in air, it will generate carbon dioxide and the water as the product. When you balance this equation, it becomes this. Let's do another one. For example, propane react with oxygen, that gives you carbon dioxide and the water as the product. We're going to balance the equation over here. So as you can see, hydrocarbons combustion product is CO2 and the water. CO2 and the water. Another reaction hydrocarbons can undergo, for example, for alkanes, we can undergo substitution reaction. When you have heat or light, methane can react with chlorine gas, and one of the hydrogens will be replaced with chlorine. So this is so-called substitution reaction. And the overall reaction, as you can see over here, one hydrogen is being replaced with chlorine, and HCl is also generated as the other product. For alkenes and alkynes, they can undergo so-called addition reaction. For example, when you have a double bond in ethene, you can add a chlorine to it. So basically what's going to happen is, for this double bond, one of this double bond is broken. So it will become a single bond in between the two carbons. And then you will need more substituents to fill out the tetravalency, and this will be the chlorine. I'll give you one more example. Right. For example, you have a CC double bond and CC single bond. Then you can also react with hydrogen. So when you look at this, it's similar. You are going to break this bond and make it a single bond out of it. Then you fill it up. Rather than with chlorine, you're going to fill it up with hydrogen, and this is so-called hydrogenation. So first, you're going to break that double bond and make a single bond out of it. The next thing you're going to do is to make sure all carbons is satisfied with tetravalency. This carbon only has 3 single bonds, and this carbon 3 single bonds. So you're going to add a hydrogen to it. Remember, if you react with chlorine, you're going to add a chlorine. If you react with hydrogen, or H2, chlorine CO2, the same thing. If you add a hydrogen, you're going to put down hydrogen for the vacant position. So we just demonstrated to you when you add hydrogen to alkenes or alkynes, it's so-called hydrogenation reaction. Let's look at another example for alkynes. For example, you have a CC triple bond. So when you add hydrogen to it, this is a triple bond. You can break one bond and it becomes a double. Then you break another one, it will become a single, or you simply break this triple bond and make it a single out of it. So let's do that. So if you add hydrogen, it will take 2 hydrogen molecules. Okay. So first thing you're going to do is you're going to break this triple bond and then make it become a single. So once it becomes single, do remember those 2 carbons, as you can see over here. This carbon only has 1, 2, 2 bonds, and the other carbon also has 1, 2, 2 bonds. So you will need 2 more hydrogens to fill up the position. So that will be the product after you do addition reaction, also called hydrogenation reaction with hydrogen. Hydrogen is being added to the triple bond. It can also be added to a double bond, as we demonstrated previously. For the double bonds and triple bonds, they undergo a specific type of reactions like a chlorination or hydrogenation. Both are so-called addition reactions. And all double bonds and triple bonds will most likely undergo this type of reactions because they are specific and they are so-called functional groups, which represent a specific type of reaction it can undergo. We have more different types of functional groups. So what is functional group? A functional group is characteristic atom or group of atoms that has been inserted into the hydrocarbon, and the functional group can usually undergo a certain type of reactions. As you can see, for the double bond and a triple bond, they can undergo addition reaction. So when you represent the functional group, a lot of times we can use G to represent the functional group and the R to represent a hydrocarbon group. For example, we can write something like this: CH3, CH2, that's a hydrocarbon group. And it's connected, for example, with another group, NH3. So NH2 rather. NH2 would be the functional group, and the left side, the hydrocarbon portion, hydrogen carbon only, that's called hydrocarbon group. Okay, all right, let's look at more examples. For example, when you look at methanol, on the left side you have CH3 group, that's methyl group, and this is hydrocarbon, it's the R group in the RG representation, and the OH group is the functional group, and this functional group is for alcohol. So sometimes we also call this OH group the functional group for alcohol. Functional group. Let's look at all the functional groups we have over here. So alcohol means the functional group is going to be OH. So connected to hydrocarbons or carbon chain. R means a carbon chain, right? Ethers, the functional group is O, but it's flanked by 2 hydrocarbon chains. Do remember, O by itself, oxygen by itself, does not guarantee you have an ether. For example, when you look at alcohol, it also contains O, but it's connected to a hydrogen directly. So this is called alcohol. But if this oxygen is connected with 2 hydrocarbons, then this is called ether. Okay. For example, when you have OH group connected with hydrocarbon, then this is so-called alcohol. And for this particular example, we call this ethanol because eth means it's 2 carbon, alcohol. OH means it's alcohol. Ether contains O but flanked by 2 hydrocarbons. You see hydrocarbons, hydrocarbons, and each one is a methyl group, so you call this dimethyl ether. We will not ask you to name these compounds, but we will ask you about the functional groups. So if you have a CO double bond connected to hydrogen, okay, through a single bond, then we call this whole group aldehyde functional group. And this CHO in the condensed formula, it's representing CO double bond connected to hydrogen through that carbon. You can also write it this way, as you can see on the left side, right over here. Okay, right. So ethanol, which has AO ending, that tells you have two carbons, and you have a functional group that has a CO double bond connected with the hydrogen. And by the way, the CO double bond by itself, it's called a carbonyl group. So when you look at aldehydes, it contains a CO double bond connected to hydrogen. However, in ketone, you also see CO double bond, but you look at the environment or how this functional group is connected is also important. It's not just the functional group itself. So in this case, the carbonyl group or CO double bond is flanked by two hydrocarbons. So you look at this CO double bond is flanked by hydrocarbons. That's why this functional group is called a ketone functional group. When you look at the name of the compound, it has ONE ending. If a CO double bond is connected with OH, then this whole functional group, this whole thing, is called carboxylic acid functional group. And this group, it can be written as COOH. Do remember, this does not mean C is connected to O and O is connected to another O. This is wrong. Rather, the structure is written on the left side. C is connected to one of the oxygens with the double bond and then connected with an OH group. Do remember, this whole group is considered as the carboxylic acid functional group. You cannot single out the OH and you call this alcohol functional group because you think the alcohol is OH. No, you have to put this together and call this whole thing as the carboxylic acid functional group. And then, as we have demonstrated to you again and again, it's not just the functional group itself, it's how they are connected. So when you look at esters, you also have a CO double bond, you have an oxygen. However, that oxygen is not OH, it's connected with the hydrocarbons. Then we call that an ester. Ester can be written as RCOOH. So look at this example. You have a CO double bond connected with an oxygen, which is connected with a hydrocarbon. Then you call this an ester. For amine is nitrogen connected with certain number of hydrocarbons. Okay. For example, this hydrocarbon over here on the left side, then you have a nitrogen connected with two hydrogens over here. So this is so-called amine. Let's look at a few practice questions over here. Which listed type of compound does not contain a carbonyl group? So carboxylic acid will contain CO double bond with OH connected. So what is carbonyl group? Carbonyl group is simply the same as saying CO double bond. So carboxylic acid functional group, it does have carbonyl included. Ether is an oxygen flanked by two hydrocarbons. So that's the functional group, but it's flanked by two hydrocarbons over here. So this one does not have a carbonyl, right? What about ester? Ester is this functional group, CO double bond connected with the O and another R. So that's the ester functional group. In this, you do see a carbonyl group. So look at ketone. Ketone means it's a CO double bond or carbonyl flanked by two hydrocarbons. Okay, so that's the carbonyl group. What about aldehyde? Aldehyde is going to be CO double bond connected to hydrogen on one end. The other end, it's a hydrocarbon. So that's the aldehyde function group. It does contain carbonyl. So B does not contain carbonyl group. What functional groups are present in the following compound? So NH2, that's an amine. Okay. COOH, COOH, it's written as COOH, folks. So COOH, remember COOH is the same as CO double bond connected with OH, and the other end is connected to something else, right? So that is carboxylic acid over here. So carboxylic acid function group. And OH by itself is called alcohol. So you do have amine, you do have alcohol, and you have a carboxylic acid. So C is the correct answer. Let's look at some examples of alcohols. Alcohols, they are the organic compounds containing OH function group, as we just talked about. For example, in ethanol, you have 2 carbons and the OH group as the function group. In 1-butanol, that means on carbon 1, you have OH group because OL means the function group of OH. We actually consume alcohol in our daily life. As you can see, beer contains about 3 to 6% of alcohol, and the wine usually contains about 12 to 15% ethanol. And spirits, such as whiskey, rum, and tequila, range from 40 to 80% of ethanol, depending on their proof. The so-called proof of an alcoholic beverage is twice the percentage of its ethanol content. For example, an 80 proof whiskey contains 40% of ethanol. So if it's a 40 proof, that means it's 20%. See that? 20% ethanol. Isopropyl alcohol is also an important alcohol. It can be purchased at any drugstore or as the rubbing alcohol. Another common alcohol is methanol. It's also called a wood alcohol because it can be made from wood. The methanol is commonly used as laboratory solvent and as a fuel additive. It is toxic and should never be consumed. About ethers. Ethers are organic compounds with the general formula as you see over here. The functional group is the oxygen itself, but it's flanked by 2 hydrocarbons. The most common ether is diethyl ether. Okay. Diethyl ether is frequently used as a laboratory solvent because of its ability to dissolve many organic compounds. The low boiling point allows for easy removal of the solvent when necessary. Diethyl ether was used as a general anesthetic for many years. And aldehydes and ketones both have carbonyl as part of the functional group. Ketone has carbonyl flanked by 2 hydrocarbons, and aldehyde has a CO double bond connected with hydrogen as the functional group. Both aldehydes and ketones, to remember, contains a CO double bond as we just emphasized. One important example of aldehyde is formaldehyde, which is a gas with a pungent odor. It's often mixed with water to make a formalin, a preservative, and a disinfectant. Formaldehyde is also found in wood smoke, which is one reason that smoking foods preserves them. The formaldehyde actually kills the bacteria. Aromatic aldehydes, those that contain aromatic arene, have present aroma. For example, cinnamaldehyde and vanillin both have aldehyde functional groups. Carboxylic acids and esters have the structure as indicated over here. And some common carboxylic acid include ethanoic acid, which is also called acetic acid, the active ingredient in vinegar. Methanoic acid, usually called so-called formic acid, is the acid present in bee stings and ant bites. Lactic acid is the acid that causes muscle soreness after intense exercise. Citric acid is present in limes, lemons, and oranges. What about esters? Esters are best known for their sweet smells. For example, ethyl butanoate is responsible for the smell and taste of pineapples. And the methyl butanoate is responsible for the smell and taste of apples. What about amines? Amines are best known for their awful odors. For example, when a living organism dies, bacteria that metabolize its proteins will emit amines. For example, a trimethylamine causes the smell of rotten fish. The triethylamine, as you can see over here, that's triethylamine. So we have spent a lot of time talking about the function groups. Hopefully by now you will be able to identify each individual function groups. So that's it for today. See you next time. Bye.